Welcome back to ECE 320A. This is the class prior to your third exam. Exam number 3 is on Thursday, which is the bottom announcement. Hopefully that doesn't shock you that that's coming up in a couple of days. To get ready for that, you actually have your last homework assignment due today. And there's some supplemental material if you're interested in maybe a little bit more detail on convolution. There's some notes and videos available with a couple of examples and the concept of flipping and sliding and intervals and limits, and making the distinction between finding the intervals when a particular overlap pattern is valid and finding or using the correct limits of integration in that interval, and they're not the same. Those two are two distinct steps or values in the convolution process. We will have, if everything is working properly, we'll have a review session after this class, and that's at 5 o'clock today in this same room. Our goals for today are to just state the process for exam number 3 and maybe talk about the topics for that exam. We'll go through some examples of sinusoidal steady state. We'll do it analytically or by just plugging in j omega for the appropriate, or in place of s in our transfer function expression. And we'll look at how to perform this computation of h of j omega naught graphically. How do we maybe gain some insight by drawing the s-plane, the poles and the zeros, finding magnitudes and angles for each of the different pole and zeros that are in our transfer function. That we can do graphically to sort of visually check your work if you're just plugging in a number and trying to compute the complex number. For exam number 3, in terms of the process, you'll have 3 sheets of notes. Those sheets haven't grown in size. They're still 8.5 by 11, and maybe you don't need that many, but that's really just to give you a new page if you've been collecting pages from exam 1 and exam 2. You can bring your standard calculator, something to write with, but no cell phones, no computers, no textbook, no class notes, no buddies, and that's why we sit in the appropriate columns on exam day. The topics which maybe we'll flesh out a little bit more in the review section or the review session after this class is really concerned with material that you've covered in homework assignments 6, 7, and 8 since exam number 2. And that deals with S-domain circuit analysis. How do you rewrite directly from the time domain circuit the S-domain circuit? And you'll need to be able to incorporate initial conditions for your energy storage devices, and it might be nice to know how to incorporate those in 2 different ways, either as series voltage sources or as parallel current sources, and to know when you might want to do either of those ways of incorporating initial conditions in your S-domain equivalent circuit. You better be able to find a transfer function for a given circuit, and when you're finding transfer functions, you don't need to worry about the initial conditions. You don't have to include these sources, either voltage sources or current sources associated with the energy storage devices. You just replace them immediately with their impedance in the S-domain and find or perform a little analysis to try to find the relationship between the output variable and the input variable so that you can now derive this transfer function. You better be able to know the different steps in convolution. I might ask you to flip and slide a waveform. And if I do, I want you to actually give me the functional description in terms of t minus lambda of the waveform that is in that problem. And if it's a sloping line, you need to give me that sloping line in terms of t minus lambda. Don't forget to include that information. I'll say include all the information that you need. Well, that and the endpoints of where things are happening are important in that one piece of a convolution problem. You should be able to know when a particular system will see a non-zero output based on when the input is applied and when the impulse response shakes or moves. And can you now find different overlap patterns, or can you now find the value of y, the output, at a particular time? And if you now can find when y of t is non-zero, now if I ask you to find y for some time outside of that range, you can immediately say, oh, y of that time is 0. Probably won't do that, but I could. And you should be able to find the sinusoidal steady state analysis, and that relies on evaluating the transfer function at a particular frequency, omega naught, where that omega naught corresponds to the frequency of the waveform that you're exciting your system with. And knowing how to do that analytically or graphically will be to your advantage on the exam. There should be plenty of review material on D2L. That, yes, question? Will you be asked to design a high or low pass filter on the exam? Maybe. It was in a homework, wasn't it?
I didn't see it up there, so it was just...
So maybe I missed that, so it wasn't on there. Thanks for reminding me. Your buddies will thank you after class. I'll escort. Pardon? That's true. They might thank you after the exam if they now see it and they go, boy, I'm glad you said something. So be ready for that. It won't be real extensive because we'll have more filter design after exam number 3 on the final, and the final exam will be comprehensive. So we'll have another section or unit on filter design. But you have had some homework problems that talk about break frequencies and finding that frequency. And that's sort of Bode plots and filter design that we'll be using after exam number 3. So I'm not sure I answered your question, but be ready for designing a low-pass filter. You should be able to do that based on all the discussions that we've had this semester. If you get into an interview, you better be able to design a low-pass filter, or at least draw a low-pass filter and find the break frequency or the pole where that roll-off begins. Here's a sinusoidal steady-state analysis example relative to a circuit. Suppose somebody says, oh, I want you to apply this particular sinusoid to this circuit, and I haven't shown you the circuit, and they are asking you now to find, so you're applying a voltage, and they're asking you to find a current, an output current, in the sinusoidal steady state. And here is your circuit. They give you, what's the order of that circuit, if you had to find that? Is it second order? I've heard 2, I've heard 5. Do I hear a 10? No. Where did those 2 numbers come from? Where did 5 come from? You have 5 energy storage devices now, don't you? Interconnected in a certain way. And generically then, if you don't have these parameter values selected in a specific way, you'll have a 5th order circuit. And what does that mean? If you know you have a 5th order circuit? Pardon? where would you see something that is connected to this answer of fifth order? Where would you expect that number to exist or live relative to this circuit? So you're going to have a fifth order differential equation. You could, and that means that if you find a transfer function associated with this circuit, your denominator polynomial is going to be fifth order, generically, if you don't have any cancellations. Maybe we'll have some cancellations in this one, and we'll have to wait and see. Okay? But now how do we proceed? If I want to now find what is my sinusoidal steady state current flowing in that rightmost branch when I apply as an input this sinusoid. And if you were looking for partial credit or maybe a site visit, and if you're doing an interview, that's maybe your partial credit. You maybe didn't get the job offer just yet, but now they were impressed that you at least knew something about how to find sinusoidal steady state. What's happening in this circuit when it's excited with that voltage? How are you shaking this circuit? At a particular frequency, aren't you? You're shaking it at 2 radians per second. So everything in here, after the transients have decayed, you should see everything shaking at that frequency. So the currents are going to shake at that frequency, 2 radians per second. Voltages, whatever you measure in this circuit, it's going to have that sinusoidal frequency. What will differ is the amplitude of that waveform and its advance or delay relative to the advance and delay of your input waveform. Meaning your voltages and currents won't be lying on top of each other with respect to peaks and valleys. They'll be offset. There'll be some phase shift. So you'll have a change in amplitude and a change in relationship of the peaks in this sinusoidal steady state output. Now, where do we go? Well, first thing we need is probably to find the transfer function, h of s. And once we have that, then we just have to turn the crank on this process, which is evaluate that transfer function at, they've taken down our tenths, so I will understand if you can't answer this problem. But now you need to walk up the imaginary axis underneath your tent, and where do you stop? At J2. You're going up the J-axis, and you stop at 2 radians per second, and you look around and you say, okay, how is this transfer function influencing me now standing at this point at 2 radians per second? And that's what happens when you evaluate h of s at that location on the imaginary axis J2. In order to get that, we need to first find h. And what is h? If it's a transfer function between the input v sub I and the output I sub 0, which one goes where in the transfer function? The output's on top, the input's on the bottom. So that if you hit this transfer function, h of s, with the input, v sub I, you'll get the output, I sub 0, out. That's a way to sort of check your work if you don't want to try to remember output over input relative to the transfer function. Now I simply resketch the circuit, and then what's the next step? in this process of analyzing or finding the transfer function between v sub I and I sub 0. And that process really just means I need to find one equation that contains s's and only v sub I of s's and I sub 0 of s's. I can't have any other signals in that expression. If I have just those two and a bunch of s's floating around, I can solve for that ratio, I sub 0 over v sub I. What do I do with the resistors? This is now my S-domain equivalent circuit. How do I populate it? Resistors don't change, so wherever I had a resistor, I don't have very many of them, but I can immediately put down a 1. My inductors are all S times the inductor's value, L, and in this case I think they were all 1 Henrys. So these now just become S's. And my capacitors become 1 over SC. One of those capacitors is 1 farad, the other one is 1/2 of a farad, so they will look a little bit different, but the first one is now this 1 over S for 1 over SC with C equaling 1, and the other one is 1 over S times 1/2. That 1/2's in the denominator, so I could say this is now 2 over S. And if I'm trying to find an expression for, or an equation that contains v sub I and I sub 0, I may not be able to do that in one step. But how might you want to analyze this circuit efficiently? I know what you, yes? Probably node voltage. You could, what I was thinking is most everybody sees 2 meshes and they want to do mesh analysis. And you could do that. You would now have mesh 1 on the left, mesh 2 on the right, and mesh 2's mesh current would be I sub 0 of S. But now you have 2 equations and 2 unknowns to solve. If instead you said, well, let me just find this node voltage, let me call that v sub 0 of S, which is not asked for in the transfer function, but as an intermediate step, I can now solve one equation in terms of v sub 0 of S. And it will contain the input voltage. So that if I have v sub 0 of S, I now know that I can find I sub 0 of S. That's just v sub 0 over the impedance in that branch where the current is flowing that I want, I sub 0 of S. I sub 0 of S is now v sub 0 of S over S plus 2 over S. V sub 0 is not what I need. I need v sub I. So can I find a relationship that contains only v sub 0 and v sub I? And that's my KCL equation at that one node that I've labeled as v sub 0 of S. KCL now says that I can look at this current and this current and that current, and all of those currents are leaving that node. They can then be summed up and set equal to 0. The horizontal current is the voltage dropped across that total impedance, which is v sub 0 minus v sub I, over that impedance, which is S plus 1. Plus the first or the middle current, which is now v sub 0 over that impedance, S plus 1 over S. And finally, the rightmost vertical current is V sub 0 over that impedance, which is S plus 2 over S. Those three currents now sum to 0, and this is my one equation that contains my independent variable, my input, V sub I, and my to be determined node voltage, V sub 0 of S. And I'm just going to find the expression. Once I find the expression for V sub 0, I can plug it in to the previous form right there. And now I have my I sub 0 of S in terms of a bunch of S's and V sub I, and I can solve for the transfer function. I assume everyone's seen the cartoon that says some magic happens. You have some professor at the board, and he's got all these formulas and equations, and then he writes down an answer. And between all of that mess and the answer, the caption says magic happens. Well, the magic here is just some algebra. I'll let you do that tonight when you can't get to sleep. So now I'm going to say some algebra. Yields the following. It gives us this transfer function, h sub 1 of s, which is now I sub 0 of s over the Laplace transform of the input voltage, and that now becomes s squared plus 1 over 3s to the fourth plus 2s cubed plus 6s squared plus 3s plus 2. Where are your zeros located in this transfer function? And I ask that because one of them is not very hard to find. It's at 0, isn't it? You're looking at the finite values of s that cause the numerator to vanish. You have a 0 at s equals 0, or a 0 at the origin. And where's your other? What values of s cause this s squared plus 1 to vanish? Plus and minus j, isn't it? So now you have zeros at, you have 3 zeros, 3 finite zeros. What's the denominator? How many poles do you have? 4. And we said this was a fifth order, so we had some cancellations that happened. Unless I did the magic wrong, which that's why you're going to check this when you go home later tonight. But if you were trying to sort of anticipate your answer, you would have said, oh, maybe in the process of doing this I did have a cancellation. Maybe there was another 0 at the origin that canceled a 0 at a pole at the origin, and now that's what gives rise to this fourth order or pole, 4 poles in this transfer function. What if I ask you to find the another transfer function? What if I said h sub 2 of s, which was v sub 0 of s over v sub I of s? Could you do that? That v sub 0 we just found, you could find that transfer function from this equation. And what would you expect to be true with it? The denominator would have at least this structure. Maybe there's another root. Maybe it would be fifth order because you wouldn't have the cancellation that you had in h sub 1. but you would have a similar looking polynomial as a factor in h sub 2. So it would behave similarly to h sub 1. The denominators are going to be the same in all of these transfer functions, unless you have some cancellations. Where are the poles? I'm guessing somebody's already factored that. That's kind of a mess. Is that polynomial monic? And have I defined monic before? Is the denominator polynomial monic? What do I mean by monic? That means the denominator, or a polynomial. If a polynomial is monic, that means that the highest power of s, it has a coefficient of 1. We've normalized the coefficient of the highest power of s to be 1. Here we would have to factor that 3 out and put it upstairs. So you could have a 1/3 in the numerator. We didn't do this, so this particular transfer function is not, or that denominator polynomial is not monic. But you could still find the 4 roots that cause that denominator to vanish. You can find the s's, the finite values of s's that cause that to disappear, and those actually become minus 0.0151 plus and minus j 1.245, almost on the imaginary axis. They have a little shift into the left half plane because you have a negative real part of 2 of those poles. The other poles are at minus 0.318 plus and minus j 0.573. Does it surprise you where those poles are located? If I now said sketch the pole 0 pattern in the S-plane, where would you locate the zeros? The zeros for H1 were at the origin and plus and minus j. Those are clean enough to locate. There's where we would locate our zeros. And where would we locate our poles? Wherever they said these are. So we have minus 0.01. I'm not going to be able to draw that very accurately, but it's at 1.24. So now it's there and there. It's conjugate. And the other one is minus 0.3, a little bit bigger than 1/2. And so it would now be about there. That would be your pole 0 pattern for that particular transfer function for h sub 1. What were we trying to do in this particular problem? Find the sinusoidal steady state response in that current in the rightmost branch. And how did we excite the system? What was V sub I of t? I hope it was 5 cosine of 2t plus 45 degrees. And we were asked to find that current in the rightmost branch. If that's the case, and we now have this transfer function, h sub 1 of s, what do we do with it? What we need is we need to evaluate this when s is equal to 2j, where that 2 is coming from this sinusoidal oscillating frequency of 2 radians per second. That's why we need h of j2. And that's really not difficult conceptually to put into the transfer function. We just replace every s with j2. We had our s, or I'm sorry, we had our h, which now we want to replace s with j2, and we had an s in the numerator, and we had a s squared plus 1. And that was then divided by this fourth order polynomial that was 3, s to the fourth, so there's a j2 to the fourth, plus a 2, j2 or s cubed, plus a 6, j2 squared, plus a 3, j2 plus a 2. You can follow all of those j's around, and eventually you will end up with a complex number in the numerator and a complex number in the denominator. Doing that, h now becomes minus 6j, and this is 26 minus j10. If I now said, okay, we're on the mall, you're underneath the tent, I want you to walk to minus 6j, where would you go? Up, down, right, left, where would I go? Home? Okay, where's home? Where's the home position? The origin? Let's say the home is the origin. Now from home, where would we walk from relative to minus 6j? You were both kind of right. J says you need to go up, but minus says turn 180 degrees from that direction. So it's really minus j and move 6 paces in the minus j direction, or to go down vertically 6. This other one in the denominator, if you're interested in it as a complex number, you would walk 26 paces along the real line, and then you would go down vertically 10. And that gives you a vector, or a direction and an angle associated with the denominator at that location of j2 for the overall transfer function. Doing that, or sketching that, allows you to maybe think about what this looks like in terms of a complex number as one complex number. Or you could divide all of that out. You could multiply by the conjugate on the numerator and denominator, however you want to do it, and you'll end up with h of j2 being 0.0773 minus j 0.201. And if you wanted to try to think what that looks like, if this is now 0.1, you would say, oh, I need to go over about 70 or about 80% of the way to point 1 in the real direction, and I need to go down a little bit more than point 2. So there is your real number. There's your complex number associated with h of j2. It has a length a little bit bigger than point 2, and it has an angle of negative. Or if you just converted h of j2 to polar form, you would see that it's now 0.215 magnitude at an angle of minus 69 degrees. And how do you use that information to obtain the answer that we want? We want I sub 0 of steady state of t. How do we use this complex number that we've now obtained for h of j2, that we're exciting the system at 2 radians per second. We now have used that 2 radians per second to evaluate the transfer function at j2. We've excited the system with this input. How do you use that information, those two pieces, to find your output, sinusoidal steady state? You scale this amplitude by how big h is at that frequency. It's not very big, and you change the phase relative to what the phase of h was at that frequency. We started with a magnitude of 5. We hit it with the magnitude of h of j2. Cosine, we're still shaking at 2 radians per second. It started with a phase shift of 45, but now we're modifying it due to the system's behavior. It's now shifting at a minus 69 degrees. And if you clean all of that up, 5 times 0.2 is 1, so a value of 1 in magnitude is close. We have 1.08 cosine 2t, and now we just take 69 away from 45 to obtain minus 24 degrees, and that would be your answer for your sinusoidal steady state current in that circuit that we started with, given that input voltage of 5 cosine of 2t plus 45 degrees. That's how you could find or use a circuit and use this concept of sinusoidal steady state. This was the magnitude of h of j2, and this was the angle. And that's how we modified the original input sinusoid to obtain the output that we were after. What if somebody now gave you a transfer function and asked a similar question? Suppose now somebody says, oh, here's a transfer function, h of s, and it's 1,000 s plus 5,000 over s squared plus 6,000 s plus 25 times 10 to the 6th. And suppose that they say, okay, that's the system that I'm giving you, that's the transfer function, and they want to now excite that or apply an input of x of t equaling 120 cosine of 5,000 t plus 30 degrees. And they may say, okay, can you find the sinusoidal output, sinusoidal steady state output of that system when excited with that input? What's the very first step you probably want to examine if somebody just hands you a system or hands you a transfer function? Okay, you probably want to make sure that that system is stable. All of its poles are in the left half plane. If it's not, you kick it with a sinusoid, it's going to go unbounded. You can hit it with a bounded input, which this is, may be big, but it's bounded, and you would have an unbounded output, and so you would never get to a sinusoidal steady state. It would just keep growing and growing and growing. Question?
For the last example, when we did the J2, when we put that in event function, it ended up on the right half of that complex plane, didn't it?
Oh, so the question was, when we evaluated h of J2, now what, and I wondered if this would confuse you, and it might, and I hope it didn't. I was trying to just graphically show where that complex number lives, or where it is in a complex plane. That's not necessarily saying that's the S-plane. Our S-plane for this example, so your question was, and it's a valid, that dot looks like it's in the right-hand side. It is, but that doesn't mean that this system is unstable. This just means the complex number that you obtain by evaluating or walking to J2 under the circus tent associated with this transfer function, which had these poles and this zero associated with it. The important thing is, where are these x's? Are they in the left half plane? If you have any on the imaginary axis or in the right half plane, I can find a bounded input that will cause the output to go unstable or go unbounded. Here, these might not be very big in their real part negative, but they will eventually decay because they have e to the minus something t in the exponent of all of these poles, or what these poles produce as far as their modes. The fact that these poles, these x's, are in the left half S-plane, that's the information that you can use to continue with the solution process. The fact that I now put another complex plane in front of you maybe confused you, but I was just trying to get you to think about what's the magnitude and angle of h of J2. And when I calculate it on my calculator, does it make sense with my drawing? If this is the rectangular form of that complex number, 0.77 in the real part, negative j.2 in the imaginary component, oh, that looks like it's maybe an angle close to 70 degrees, and its length is a little bit bigger than 0.2. I can now do the Pythagorean theorem to find the length of the hypotenuse, and I can find the angle with just the inverse tangent. So that's the connection, disconnection I need you to make in terms of drawing that particular diagram. In this case, where were we going? We wanted to check where are the x's associated with h of s. Where are the poles? And here's a time-saving step. If you have a quadratic, let's say you had a sixth order denominator and somebody had graciously factored it into 3 quadratic polynomials that were multiplied together. And they said, is this system stable? And you go, I don't know. I'm going to check each of those 3 quadratics and see if they all have their roots in the left half of the complex plane. If you now have a quadratic, a second order polynomial in S, and it's monic, is this one monic? Yes. So this is monic because this coefficient is 1. If you've now normalized that quadratic to be monic, now all you have to do to make sure that it has, without going through the quadratic formula or plugging it into your calculator, you just need to know, are both of these other 2 remaining coefficients present? Do they exist? And are they positive? And in a future class, you can learn why that's true, but you could just convince yourself with a few examples through the quadratic formula and see that as long as these 2 coefficients are present and positive, that polynomial has its roots in the left half plane. It has negative real parts. And that's the conclusion I'm going to make here. I can now say that h of s is stable because the coefficients of the denominator, that's what influences stability, are the poles or the denominator roots, are present and positive. And we can use that because we had a second order polynomial that was monic. Now we have a question.
So does it just matter if the first degree coefficient is positive? Because I feel like as long as the signs are, like as long as they're all positive, that
So now what you want to make sure is that these 2 the question I think was, doesn't it just matter on the linear coefficient, the sign of that? No?
like why does it matter if it's a 1 rather than it just being positive?
Oh, so as long as the leading coefficient is positive, you can reach the same conclusion. I'm just saying let's all just normalize the leading coefficient to be monic, and then we all have a quick way of saying, oh, it's a monic polynomial. I don't have to say the leading coefficient was positive in sign. But as long as the leading coefficient is positive, you can factor it out and say, oh, are the remaining 2 coefficients present and positive, then I'm good. Yes, so it can be that the leading coefficient just needs to be positive, but that's sort of another condition. I guess I'm using it also by saying it's monic. But this way you say a second order monic polynomial, the other 2 coefficients need to be present and positive, and you have your result. You can say that all the roots are in the left half plane or they have negative real parts. Now that we know h of s is stable, what do we do? Or what do we focus on now? If we want to find what's the y of t in the steady state, and I'm applying this sinusoid to it, what can you expect out of the output? If you wanted partial credit, what would you do? If you said y of t in the steady sinusoidal steady state, so sub ss, is equal to, what would you quickly write down? Okay, you could write down the formula, couldn't you? Let's say you didn't have time. What's the first thing you want to maybe identify? You need to identify the frequency that you're shaking this system at, don't you? That's the key piece of information. You need to find omega naught. Or you're now saying, this is my key piece of information. There's omega naught. And so now omega naught is 5,000 radians per second. Once you have the transfer function with all of its poles in the left half plane, it's stable. You know the input is shaking at 5,000 radians per second. You can now you can calculate J5000. And in our case, we had a transfer function of 1,000 S, so there's the J5000 plus 5,000 all over S squared plus 6,000 S plus the constant, 25 times 10 to the 6th. Whoops. And some of these numbers actually clean up. We have 6 zeros in the product of the numerator. There's a 10 to the 6th. We have 5 plus J5. That has equal real and imaginary parts, so we have an angle of 45 degrees and a length that gets expanded by the square root of 2. The numerator now is 5 square root of 2 times 10 to the 6th at an angle of 45 degrees. The other one, J squared, is minus 1, and you now have 5,000 squared. That's just 25 times 10 to the 6th, and we're subtracting it from 25 times 10 to the 6th. Well, that cleans up, and all we're left with then is the 6,000 times J5000. And where is that? If this now has canceled that, what's the angle of 6,000 J5000? That's 90 degrees, isn't it? And those 10 to the 6ths cancel. And we have the square root of 2 over 6 factoring a 5 out of 30. And now how do we combine our angles? We subtract the denominator from the numerator, and we're left with minus 45 degrees. And now we can write down our output. Y, our output in the sinusoidal steady state, is the magnitude that we started with, 120, scaled by h of J5000's magnitude, cosine. The output is 5,000 t. It's moving at the same frequency as the input, plus 30 degrees minus 45 degrees. Or if we do a little bit of canceling there and combining here, we then end up with our sinusoidal steady state output being 20 square root of 2 cosine 5,000 t minus 15 degrees. Yes? I didn't tell you the units. The question was, what are the units? I didn't give you units on h of s, so you don't even know what y is. X, I didn't specify what the units were on that. H, I didn't tell you what h had for units. So you're just going to say, oh, y sub sinusoidal steady state is this. And I don't know if that's a voltage. I don't know if it's a current. Maybe we're not even in an electric circuits class. And maybe that's a position of something, and it's moving based on possibly the input was a voltage, but now the transfer function is converting that voltage into a position, and this now might be in meters. Who knows what that transfer function was? Let's talk briefly about, I think I mentioned, if you give me a system, a transfer function that has any pole on the imaginary axis, I can find a bounded input that will cause an unbounded output. Where did that statement come from? So let's look at this bounded input, bounded output concept. Or if you are given a bounded input, do you have a bounded output? Suppose somebody gives you the following transfer function of a system, and let's say it's 5 over s squared plus 1. Where are the poles of that transfer function? You can draw better than I can. They're supposed to be at plus and minus j. My upper pole looks like it missed the imaginary axis a little bit, but it's there. Now, if you now have your system that possesses poles on the imaginary axis, can you think of an input that would cause an unbounded output? Can you now hand me an input that when applied to this, and the input is bounded, but now when applied to this system, you can make the output grow as a function of time? And here's something to think about. What if you walked up and energized the energy storage elements in this system and let it go? What would happen? It would oscillate forever, wouldn't it? And how would it oscillate? Do you see the omega? What's omega? What's its frequency of oscillation? Exactly. It's 1 radian per second. You now have a system that likes to naturally move or shake at 1 radian per second. How would you expect to now encourage that with a bounded input that would maybe increase the energy in the output? Think of a swing. Can you push a swing at a certain rate and get the guy or girl to go higher and higher in that swing? No, you can't do that. Well, pick an ideal swing that has no friction. Okay, maybe that was a bad analogy, but if I'm now kicking this system with a bounded input, what frequency do you think I should encourage it with if it naturally likes to move at 1 radian per second? 1 radian per second. Now you know what the bounded input is. The x, to make this go crazy, would be to say, oh, I can find a input that has poles right on top of the poles of the system. And you can inverse Laplace transform that to find the time domain version of that signal. This is now a bounded input. What is x of t? Okay, it's going to be on your crib sheet, but you should be able to find this or remember this. Is it cosine or sine or both? My head's going to explode. That's why I need my crib sheet. Which one is it? It's a sine. Why do you say that? It's sine because you don't have an s in the numerator. You just have an omega. This is now sine, in fact, if we wanted to inverse Laplace transform this. So this is now sine of 1t. That's bounded. That's just, and that's what I could now excite my, and what's y of s look like? Y of s, now we're in the frequency domain. It's h of s times x of s. H of s was 5 over s squared plus 1. X was 1 over s squared plus 1. Now I have 5 over s squared plus 1 squared. And find that in the table, and what are you going to end up with? Irrespective of what this coefficient is, you're going to have a t sine of t. Or a t cosine of t if you actually had an s in the numerator. Or a combination. But you're going to have a t, and what's that do as time gets bigger? It just keeps growing and growing. So you're not going to reach a steady state. What if, well, now you can see that even if you had a integrator, a pure integrator, where would its pole be? If you had a system and you build an integrator, so now it takes as an input something and integrates it. What's that look like in the frequency domain? Has convolution in the time domain, but now it's the inverse of differentiation. Differentiation is multiplication by s, integration is division by s. So if this is your system, if your system is a pure integrator, what could you hit that or apply to that integrator and cause an unbounded output? What could you integrate that's bounded that would go unbounded in the output of the integrator? What's the frequency of this associated with this, if you wanted to think about it? Where is this? This is at home, isn't it? This is at the origin. That's DC. Just hit it with a constant. Hit it with a unit step, and that's going to give you a y of s of 1 over s squared, which is t. It's a ramp. The input now that would cause you issues is x of t is a constant. It could be a 4. It could be 2.7. It could be e, a constant. Now y of s is equal to h of s x of s, which is 1 over s squared y of t is t. That's not bounded. Now, I promised we would do some graphical drawing today. Let's look at graphical evaluation. Of this transfer function at a particular frequency. And to do that, let's go ahead and pick a transfer function. Let's say we now have h of s is 1,000, s plus 5,000, and in the denominator I'm going to factor it to look like s plus 3,000 squared plus 4,000 squared. Can you see the poles in that factored form? Or is your system stable? Are the poles in the left half plane? I'm asking you the same question, just different ways. If I now said rewrite h of s to have poles as complex conjugates if that's what they equal. The numerator is already factored into a 0. You can explicitly see that 0 is at s equal to minus 5,000. But the way that I've factored the denominator, that says that I actually have a real part of minus 3,000. Or my poles are at s plus 3,000 minus j 4,000 and s plus 3,000 plus j 4,000. And where is this pole located? In which quadrant? First, second, third, or fourth? Now you need to find the value of s that causes that factor to disappear or to become 0. It now has a real part of minus 3,000 and an imaginary component of plus j 4,000. That puts you in the second quadrant. So this pole in second quadrant, where's this pole? It better be the conjugate of the one you just found, and that's the one just below. So this pole is in the third quadrant. Now we can sketch those. Here's my S-plane, and I'm going to go ahead and scale that by 1,000 so that now this is 1,000 in the J direction, this is 2,000, 3,000, and this is now minus 1,000, etc. So that this is now minus 5, and that's where my 0 was located. My poles were at minus 3,000 plus and minus j 4,000. So I need to get one more grid line. And suppose I want to find or evaluate this h at j2000. Where am I underneath my circus tent? If I want to evaluate that transfer function at j2000. J is where? That's in the vertical direction, and I didn't say any real component, so I'm living on the imaginary axis, and I didn't give you a negative. I'm now right here. Whoops, I wanted that. Well, and what am I going to do? I'm going to find all of the contributions of these poles and zeros. I need to find the distances that each of these are from that triangle and their direction. This now has a negative angle. I could say this is theta p1, and this is the length from that first pole down to that location. I have this direction of my 0 with a length of L sub z, and you can find that by Pythagorean theorem. It's 5 squared plus 2 squared, square rooted. Again, we've scaled this all by a factor of 1,000. And what's the length from the pole in the second quadrant to that point J2? We walk over 3 paces in the real direction, 3 squared, and we go down 2. So it's 2 squared, isn't it? And what about the LP2 and its angle? We walk over 3 in the real direction and we go up 6. So if we wanted, relative to these lengths and angles, if we wanted h of J2000, then we would say, oh, h of J omega naught, where omega naught is the 2000. This is now, we have our given constant of 1,000. We can't forget that. But then we had J omega naught plus 5,000, where this is now going to be the 2,000. And do you see that that was exactly what we would have as a complex number if we started at the 0 and we walked right 5,000 steps and J2000 up to J2000. That gives us the exact location or way of getting from that 0 to that question or that triangle in question. What about the pole in the second quadrant? We have J omega naught plus 3,000 minus J 4,000. So now if we walked to the right 3,000 in the real direction, we go down 4,000, that's the minus J 4,000, plus J 2,000, we're back to that triangle. And that's just this length, LP1, at this angle, theta P1. And finally, the factor associated with the pole in the third quadrant, we have J omega naught plus 3,000 plus J 4,000. Or, in terms of what we sketched, we would have 1,000 times the length from the 0 at that angle of the 0. The second quadrant pole is LP1 at an angle of theta P1 and LP2 at an angle of theta P2. And what we had, if we wanted to look at one of those in particular, if we looked at the 0, in more detail, which I've already tried to talk our way through, we had that 0 here at minus 5, and we were trying to get to that triangle. We wanted this distance away, and we wanted to move in that direction. LZ is now just this square root of 2 squared plus 5 squared. And we've scaled everything by 1,000. So this is now the square root of 29 times 1,000. Or that becomes, if a little bit bigger than 5.385 times 1,000. And what's theta z? Now you may want to bring a protractor to your exam, But you can calculate that. You know you're going, oh, that's a pretty bad tick mark, but you're up 2 and you're over 5. So the inverse tangent of opposite over adjacent. Theta sub z is now the inverse tangent of opposite 2 over adjacent, which is 5. And if you'd drawn it accurately, you could sort of eyeball, oh, that was about a 22-degree angle to get you from that 0 to that position of J2. And if you put all of those pieces together, how do you combine your angles? You have all the 0 angles summed up, and you subtract all of the pole angles. How do you combine the lengths? You just multiply and divide. And that gives you h of J2000. And once you have that, you know how to use it to find the sinusoidal steady state. You take the magnitude and the phase to adjust your original input's sinusoidal waveform. That should get you through exam number 3. Okay? I'll see you Thursday for the exam, if not before.